Hello friends, welcome you all to the 24th lecture on functional analysis and its applications. In this lecture, we will discuss the dual space of L1 is L infinity. Content: the dual space of L1 is L infinity. Dual space also known as conjugate space. Theorem: the conjugate space of L1 is L infinity. That is L1 star equal to L infinity. Proof: let infinite dimensional vector x belonging to L1, so that if x is in L1, then summation n is equal to 1 to infinity mod xn less than infinity. That is, summation of mod xn should be bounded. Okay, we know that if x belonging to LP, then summation n is equal to 1 to infinity mod xn power p less than infinity. Okay, here p is 1, so if x belonging to L1, then summation n is equal to 1 to infinity mod xn less than infinity. That is, this is the convergent series. If we consider the standard basis En, we can write any sequence x1, x2 and so on xn, and after xn 0, 0, 0 in the form summation k is equal to 1 to n xk ek. Okay, this is very simple. This vector can be written as this one. Okay, here x is x1, x2 and so on xn, and after xn, xn plus 1, xn plus 2 and so on. Okay, and here this vector as summation k is equal to 1 to n xk ek, then x minus summation k is equal to 1 to n xk ek. Okay, that is this one minus this. Okay, so we have 0, 0, 0 up to n, and xn 1 plus 1, xn plus 2 and so on. Here value of this is infinite dimensional vector 0, 0, 0 up to n times 0, and then x n plus 1, x n plus 2 and so on. Now, norm of this vector x minus summation k is equal to 1 to n xk ek. This is defined as infinite dimensional vector this. So, this is in L1. Hence, this vector can be written as summation k is equal to n plus 1 to infinity mod xk. Okay, very simple. Equation 2. The right hand side of equation 2 represents the remainder after n terms of convergent series 1. Hence, xk tend to 0 as n tend to infinity. That is, summation mod xk k from n plus 1 to infinity converges to 0 as n tend to infinity. Okay, equation 3. Since this converges to 0, it means norm this one tend to 0, and we know that if norm x is equal to 0, if and only if x is equal to 0, this is the property. Okay, using this property, we have x minus summation k is equal to 1 to n xk ek tend to 0. Hence, x is equal to summation k is equal to 1 to infinity xk ek. Equation 4. If f belonging to L1 star and let Sn is equal to summation k is equal to 1 to n xk ek, then equation 4 shows that Sn converges to x as n tend to infinity. Okay. Since f is linear, then f of Sn equal to summation k is equal to 1 to n xk f of ek. Okay. Since f is continuous and Sn converges to x, so here Sn converges to x, it means we have Fsn converges to Fx as n tend to infinity, which gives Fx is equal to summation k is equal to 1 to infinity xk f of ek. Equation 5. Equation 5 gives the form of the continuous linear functional on L1. Let us take f of ek is equal to alpha k and show that mapping T such that L1 star to L infinity, given by Tf equal to alpha 1, alpha 2 and so on, alpha n and so on. Okay. F is the element of L1 star. Okay, continuous linear function on L1. So f belonging to L1 star, then Tf is the element of L infinity. So let us take f of ek equal to alpha k and show that the mapping this T such that L1 star to L infinity given by this is an isometric isomorphism of L1 star onto L infinity. First we show that the mapping is well defined from L1 star to L infinity. For this, let x belonging to L1, where x is equal to beta 1, beta 2, beta 3 and so on, beta n, and after that n terms 0, 0, 0 and so on, and beta k defined signum function of alpha k bar. If k is equal to 1, then beta k is equal to this. If k not equal to n, that is 0. Using the property of signum function, we get from the above results alpha k into beta k. Okay, that is alpha k signum alpha k bar. Okay, from the property of signum function, we have mod alpha k. Okay, mod alpha k if k equal to n. Okay, so mod alpha k, we can write supremum of mod alpha k or max of mod alpha k. Okay, k lies between 1 to n. Okay, since we can write x equal to summation k is equal to 1 to n beta k ek, equation 7, we get f of x equal to summation k is equal to 1 to n beta k f of ek. Okay, and also we know that f of ek alpha k. Okay, so we can write f of x equal to summation k is equal to 1 to n alpha k beta k. Using equation 6, fx equal to summation k is equal to 1 to n alpha k beta k. So putting the value of alpha k, beta k in this equation. Okay, we have fx is equal to summation k is equal to 1 to n mod alpha k. Okay, so here we ignore all alpha k, only we take at k is equal to 1, that is maximum value. Okay, so we have summation k is equal to 1 to n mod alpha k is max of alpha k. Okay, we know that x belonging to L1, then mod of fx less or equal to norm f norm x. Okay, f is continuous linear functional. So mod fx less or equal to norm f norm x. Since x is equal to beta 1, beta 2 and so on, beta n 0, 0 and so on. And using equation 6, we get norm x equal to summation k is equal to 1 to infinity mod beta k, because here vector x defined this beta 1, beta 2 and so on, beta n 0, 0, 0. So norm x equal to summation k is equal to 1 to infinity mod beta k. Okay, add this property beta k. If k is equal to 1, then signum function of alpha k bar, otherwise 0. So only one term at here, signum alpha k bar. Here modulus, so value of this is modulus of signum alpha k bar. Okay, modulus of signum alpha k bar is 1. From equation 9 and 10, okay, so mod fx less or equal to norm f into 1. Okay, here norm x is 1. That is here mod fx, that is mod of this. Okay, here already mod alpha k. Okay, so max value of this is max mod alpha k or simply mod alpha k. So simply mod alpha k or this can be written as mod of fx. Okay, so mod fx equal to max of mod alpha k and mod fx less or equal to norm f norm x. Okay, and norm x is equal to 1. So mod fx less or equal to norm f. Okay, so mod fx defined by max of mod alpha k or supremum of mod alpha n. Okay, here 1 less or equal to k less or equal to n less than infinity. So n lies between 1 to infinity. So it can be written as supremum of mod alpha n less or equal to norm f. Okay, so this is bounded by norm f. This implies that alpha n is the element of L infinity. Okay, alpha n, which is the image of f under T, belongs to L infinity. So T is well defined. Next, we show that T is onto L infinity. Taking beta k belonging to L infinity, we have to prove that there is G belonging to L1 star such that T maps G onto beta k. If x belonging to L1, we have x is equal to summation k is equal to 1 to infinity x k e k. We show that the required G is given by Gx. G is linear functional. So Gx equal to summation k is equal to 1 to infinity x k G of e k, that is beta k. Okay, so we show that the required G is given by Gx equal to summation k is equal to 1 to infinity x k beta k. Since the representation of x is unique, G is well defined, and further it is linear on L1 to show that G is bounded. Here consider mod Gx equal to mod of summation k is equal to 1 to infinity xk beta k, and this is less or equal to summation k is equal to 1 to infinity mod beta k xk. So if we expand this, mod of beta 1 x1 plus mod of beta 2 x2 plus and so on beta k xk plus and so on, okay, up to infinity. So each beta k is equal to 1 to n. If we replace each beta k by max beta k, okay, and max beta k can be common, okay. So it can be written as summation mod beta k xk less or equal to max of beta k into summation k is equal to 1 to infinity mod xk. This is norm x. Therefore, mod gx less or equal to mod beta k xk, and value of summation mod beta k xk is this one. So we can write mod gx less or equal to max of beta k into norm x. This shows that G is bounded, okay. Since Ek belonging to L1 for k equal to 1, 2, 3 and so on, we get G of Ek is beta k for every k. Hence Tg equal to beta k. K is equal to 1, 2, 3 and so on, that is beta 1, beta 2 and so on. And T is on L1 star onto L infinity. Next, we show that norm of Tf is equal to norm of F, so that T is an isometry. Since Tf is the element of L infinity, we get from equation 11. Supremum of mod alpha k lies between 1 to infinity, equal to norm of Tf, okay. Value of this is norm of Tf and this is less or equal to norm of F. So we can write here supremum mod of alpha k, which is norm of Tf, this is less or equal to norm of F as equation 11. Now to prove the reverse inequality, okay, reverse of this. Let x belonging to L1 so that x equal to summation k is equal to 1 to infinity xk ek, okay. Hence f of x equal to summation k is equal to 1 to infinity xk f of ek, okay. Since f is linear functional, so we can write, and f of ek is alpha k. So mod of fx, mod of this equal to mod of this, that is mod of summation k is equal to 1 to infinity xk alpha k. So taking supremum of alpha k, this less or equal to supremum of alpha k into summation k is equal to 1 to infinity mod xk, that is norm x, okay. So we can write this inequality as mod fx less or equal to supremum mod alpha k into norm x for all x. This inequality divided by norm x, okay, which implies that supremum of mod fx upon norm x less or equal to supremum of mod alpha k, okay. This is divided by norm x, okay. So right side only supremum of mod alpha k, okay, and supremum of mod alpha k is norm Tf, okay. this one. Hence, meaning of this is norm of f. So using the definition of norm of f in this inequality, we have norm f less or equal to norm of tf. Okay. So from 12 and 13, here norm tf less or equal to norm f, and in 13 norm f less or equal to norm of tf. So from 12 and 13 we have norm f is equal to norm of tf. From the definition of T, it is linear. Since it is an isometry, it is 1 to 1. We have already proved that it is onto, so that T is an isometric isomorphism of L1 star onto L infinity. In other words, L1 star equal to L infinity, which completes the proof of the theorem. In this lecture, we have discussed the conjugate space of L1 is L infinity. That is, L1 star is equal to L infinity. These are the references which have been used in this lecture. Function analysis, Dover publication by George Beckman and Lawrence Naresy. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publisher, written by V.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.